Hello everyone, I'm Matthew Fishman. I'm an associate data scientist at the Flatiron Institute in New York, and today I'm going to be talking about what's new in ITensors.jl. ITensor is a software library for performing tensor network calculations. It was originally written in C++ and ported to Julia starting in 2019. So far, iTensor has been used in over 400 published research articles, mostly in the field of physics, but some are in machine learning. ITensors.jl was originally released in May of 2020, and we've reached 0.2 in June of 2021. Please go to the itensor.org website to get more background on the iTensor library and take a look at our recent paper and the 2019 JuliaCon talk. So iTensor is a tensor library with a memory-independent and dynamic interface. It supports dense, diagonal, and multi-threaded block-sparse tensors as well as a GPU backend. The goal of the library is to provide building blocks for easily performing tensor network computations. Tensor networks are low-rank approximations for very high-order tensors, so they could be useful in any situation where you have very high-order tensors which might have a low-rank structure. The organization of the library builds on an opaque tensor storage backend, which could have dense, block-sparse, diagonal, or other sparsity patterns, and provides a common high-level interface for performing operations like tensor contractions, from which we can build up more complicated tensor network algorithms. The unique part of iTensor's interface is the memory-independent interface where the dimensions have certain labels. So in standard Einstein notation, such as in Python's einsum or Julia's tensor operations, in order to perform a tensor contraction, you have to specify the labels of the dimensions which will contract with each other, and common labels will contract. However, if you're performing computations where you use many of the same tensors over and over, you have to rewrite these labels over and over and over, and it's easy to make a mistake. So for example, we've made a typo in the last line here, and it can take some time to figure out where the typo is. iTensor solves this problem by storing labels which have unique identifiers in the tensors themselves. So then iTensor knows which dimensions to contract with each other, and you can have a very simple interface for writing tensor contractions where you're using the same tensors over and over. So in this talk, I'm not going to go into too much of the background of iTensor because that's covered elsewhere, and I want to focus on new features that have been added and related packages that have built upon iTensor since the 0.1 release. So for example, I'm going to discuss multi-threaded block-sparse contractions, the GPU and T-Bliss contraction backend, a quantum circuit simulator, tools we've provided for tensor contraction sequence optimization, interactive visualization tools, and a variety of other packages that we've been working on. I want to point out that, for those who don't know, the ITensors.jl now supports multi-threaded block-sparse contractions, which is a feature that we've had for a little while in the C++ version. So essentially, if you initialize a block-sparse tensor that you want to contract, and you start Julia with a certain number of threads, and you enable threaded block-sparse contractions, when you perform a tensor contraction, we will multi-thread over some of the blocks which will contract with each other, and you can get a decent speed up. So here we get a 3.5 or 3.4 times speed up for 6 threads. Now there's a lot of improvements we can make. We want to extend block sparse threading to other operations, such as tensor decompositions. We would like to improve the implementation so that it scales better to more threads. I also want to emphasize that we have a GPU backend for ITensor in the ITensors.jl library, which is primarily written by Katie Hyatt when she was at the Flatiron Institute as a postdoc. Currently, it only works for dense tensor contractions, but we would like to add support for block sparse tensor contractions on GPU as well. And we also have a tbliss backend, which accelerates dense tensor computations. Essentially, tbliss is a permutation-free tensor contraction backend. And Jinghua Liu added an Octavian backend for fast tensor contractions for non-blast float element types. In recent versions of ITensor, we also added a general quantum circuit simulator. So essentially, it's a high-level interface where you can specify a set of an initial state that you'd like to evolve with a quantum circuit. You specify a list of quantum gates that you'd like to apply to certain sites of your state or certain qubits, and you run the apply function up to a certain approximation, and you can do high-level operations like measure the resulting wave function or sample from the wave function. Building on top of that functionality, in collaboration with Giacomo Torlai, who is now at the AWS Center for Quantum Computing, we built a package called PastaQ.jl, which also adds on features like simulating noisy quantum circuits, as well as learning pure and noisy state and processes using state-of-the-art tomography techniques to learn quantum states and processes from data directly from a quantum computer. So here's a short script showing an example of running a noisy circuit evolution with a specified noise model. So please check out PastaQ.jl if you're interested in that functionality. We've also written an interactive visualization tool for ITensor called ITensorsVisualization.jl, built on top of Mickey.jl and NetworkLayout.jl, where you can, if you have an ITensor code which performs a certain tensor contraction, you can add the macro @visualize, and so ITensor will perform this tensor contraction, but also pop up a Makey window, which shows which indices of the tensor network are contracted with which tensors, which is very helpful for debugging your code if you've made a mistake in the tensor contraction you were trying to perform. In addition, we've added some functionality for performing contraction sequence optimization. So the problem of contraction sequence optimization is that if you have a tensor network diagram like this, you don't know what the optimal sequence for contracting the tensors is. So you might want to contract tensors. You could try to contract tensors C with D with each other first, or C with E. And those have different costs, and it's actually an exponentially hard problem to determine the optimal sequence that you contract these tensors in down to a scalar. And so there's a module of ITensors called contraction sequence optimization, which gives tools for automatically searching through these contraction paths and determining the optimal sequence. Now, right now, it's limited to something like 20 to 30 tensors in your diagram. but we would like to use more sophisticated algorithms, which are available in Python packages like Cotengra, as well as in Python packages like AutoHoot, which I'll talk a little bit about later. Another feature that has been primarily spearheaded by Miles Studenmeyer of the Flatiron Institute, as well as Jing Chen of the Flatiron Institute, is automatic fermion sign support. So for tensor networks which represent fermionic degrees of freedom, if you exchange indices of a tensor, such as with a permutation, you can introduce minus signs in certain blocks of the tensor. And so the idea is that usually in tensor network algorithms, people have inserted these minus signs mostly by hand, but we would like to automate the process of inserting those minus signs. So that's something that's available in an experimental feature which you can use with ITensors.enable auto fermion. And so you can see here's an example of a fermionic tensor where if we permute the indices, the block of the tensor picks up a minus sign. So this will help a lot in automating studying fermionic tensor networks with higher dimensional network topologies. In addition, we're pushing hard on adding automatic differentiation support to iTensor through packages like ITensorsGrad.jl, AutoHoot.jl, as well as a more recent iTensor network AD.jl. And this has been in collaboration with a summer intern we have, Lunjun Ma from UIUC. And so an example is that we might want to take the derivative of a tensor network like this, which is just a trace of two matrices which have a parametric dependence on the same variable. So we can write fairly simple iTensor code like this to perform that contraction, and then using Zygote by adding primitives for using chain rules for these types of operations, we can take the gradient of this tensor contraction and some functionality we'd like to add, which is mostly done by Lunjun Ma, is doing high-level analysis of taking the gradient of a closed tensor network in order to cache intermediate results. So the idea is that there's a package called AutoHoot, which was written by Lunjun and a collaborator, which he's wrapped in Julia, which turns an iTensor expression into an einsum expression like this, and then can take the gradient of that einsum expression and then determine what the tensor contractions which are common between a series of gradients. And so a lot of this functionality is going to be wrapped in a high-level package which we're working on called iTensor network AD.jl, which will provide a high-level interface for computing these gradients and then doing optimizations of large tensor networks. Another package I'd like to point out that is in development is called iTensor infinite MPS.jl. So the idea of this package is to provide a high-level convenient interface for working with infinite tensor networks. So these are low-rank approximations for infinite order tensors. And these are tensor networks that show up often in physics applications where you have translational invariance, as well as in machine learning applications. So keep an eye on that. We have some basic functionality for optimizing infinite MPS networks working at this point. Another package that we're working on is ITensors.jl, which the goal of this package is to provide high-level functionality for initializing and contracting and manipulating high-dimensional tensor networks. So tensor networks which aren't just in a linear network topology, but for example, square lattice of tensor networks or a more general lattice of tensor networks. And it provides tools like what's visualized here, where we take a tensor network which might be intractable to contract as it is and find an approximation for that network which is equivalent to a tree tensor network which is tractable to contract. And so we're working on incorporating automatic differentiation into this in order to, once we have this approximate tractable network, to optimize the tensors of this tractable network. Another more physics-related package that I'll just mention briefly is ITensors.jl, which provides tools for converting non-interacting quantum states into tensor network representations, which can be useful if we think that this non-interacting quantum state is a good starting point for optimizing an interacting quantum state. So you can see here that in a few lines of code we can create a starting state which gives us a much better initial guess for an optimization that we're performing. So the top is just from a random starting state, and then the bottom is from our guess state. So the guess state is already a very good, the non-interacting guess state is already a very good starting point for our optimization. Another small package that we've added, which is being used in ITensors.jl right now, is called serialized element arrays.jl. The idea here is that we might have a vector, imagine a vector which is storing a bunch of tensors which are too large to store in memory together. So we store them each serialized to files on disk, and then we only access certain tensors that we need temporarily and put them in memory. And so this can allow you to do computations which wouldn't fit entirely in memory. And there's a lot of room for improvement in this package, like performing memory caching of recently accessed elements, because of course, as we know, reading and writing to disk can be slow, so it would be nice to automate the process of saving certain tensors in memory if they fit in memory. So you can access them multiple times and it can still be fast. So just to summarize what we've discussed, I gave a very brief introduction to ITensors.jl, which is a high-level package for performing tensor network computations, and I've gone over some recent high-level features that we've added since the initial release of the 0.1 version in 2019, such as multi-threaded block sparse contractions, which is available in ITensors.jl, a GPU and T-Bliss contraction backend, which is available in ITensors.gpu.jl, or by loading the T-Bliss .jl package. High-level interface for simulating quantum circuits, as well as analyzing the outputs of a quantum computer using tomography, which is available both in ITensors.jl as well as POSTQ.jl. Tensor contraction sequence optimization, which is available within a module in ITensors.jl, as well as in external packages that we're interfacing, such as autohoot.jl. An interactive visualization tool called ITensorsVisualization.jl, a package for studying non-interacting particles as tensor networks called ITensor Gaussian MPS.jl, as well as tools for conveniently working with tensors that are, or other objects which are serialized on disk in a package serialized element arrays.jl. And then I briefly discussed some high-level automation tools, such as automating studying tensor networks with anti-commuting degrees of freedom, as well as high-level tools for efficiently performing automatic differentiation for gradient-based optimizations of tensor networks in these packages such as ITensorsGrad.jl, autohoot.jl, and ITensorNetworkAD.jl. In addition, we've been working on packages for studying infinite tensor networks such as ITensorInfiniteMPS.jl, as well as packages for studying tensor networks with arbitrary network topologies in this package, ITensorNetworks.jl. And so a big theme of what we're going to be working on in the near future is more tools for automating the optimization of arbitrary tensor networks. So keep an eye out on the development of these packages if you're interested in those kinds of topics.